Hello everyone, my name is Vyvyan and I'm doing PhD in Chemistry at UNSW Sydney, Australia, and you are watching my YouTube channel. Today in this video I'll be talking about how we can get information from UV visible spectrum, or how we can interpret the UV visible spectra, or what information we can obtain from the spectrum of a typical UV ultraviolet spectrum. Okay. And for that I am following a spectroscopy book written by Pavia and co-authors. So it's a spectroscopy book, and if you require this book in the PDF format, then please feel free to drop down your email below in this video. Then I'll contact you and send you the book by email. If you are listening my channel first time, then please have a look at my channel. I have uploaded more than 107 videos on my YouTube channel so far, and the range of videos related to several organic chemistry topics such as retrosynthesis, natural products, spectroscopy including NMR, IR, UV visible, and reaction mechanism, name reactions, organic chemistry, natural product chemistry, polymer chemistry, heterocyclic chemistry. Moreover, besides chemistry, I have uploaded videos related to research topics such as how to write a research paper and how to write a review paper. And also, if you are a candidate and looking to apply for PhD admissions and scholarships, then I would recommend you to watch my video about how to apply for admission and scholarships for Australia, Canada, and UK. And in that video I have described the procedure and eligibility criteria plus step-by-step guidelines. Moreover, I have made one video regarding how to write an effective email to foreign supervisors to get acceptance for SIP, postdoc, or PhD admissions. Please have a look at my channel, and then please don't forget to subscribe and share the link with your friends. If you have already subscribed, I thank you so much. Let's get back to the topic, that is what to look for in an ultraviolet spectrum, a practical guide, and I am following the book written by Pavia. Okay, and it is often difficult to extract a great deal of information from a UV spectrum used by itself. It should be clear by now that a UV spectrum is most useful when at least a general idea of the structure is already known. In this way, the various empirical rules can be applied. Nevertheless, several generalizations can serve to guide our UV data. But if you are not familiar with the UV ultraviolet spectroscopy, then I have made a bunch of videos related to this topic on my YouTube channel. Please go to my channel and watch those videos first, then come back to this channel, because almost we are finishing this chapter. This is chapter 7 from the Pavia. These generalizations are a good deal more meaningful when combined with infrared and NMR data, which can, for instance, definitely identify carbonyl groups. As you know that carbonyl groups are present in several functional groups of organic chemistry such as aldehydes, ketones, carboxylic acids, esters, anhydrides, acid chlorides, amides. Double bonds UV visible spectrum can help us to identify carbonyl groups, double bonds, aromatic systems, nitro groups, nitriles, enones, and other important chromophores. What is a chromophore? I have already made a video about this. In the absence of IR or NMR data, the following observations should be taken only as guidelines. Number 1. A single band of low to medium intensity, having intensity from molar absorbed from 100 to 10,000 at wavelength less than 220 nanometers usually indicates N to sigma star transition. That's a key information that you can obtain. That if you see a single band of either low or medium intensity and the wavelength that it appears is around less than 220 nanometer, that means that that band is due to the N to sigma star transition. For example, this is the typical UV visible spectrum. On the x-axis we have the wavelength lambda in nanometers, and on the y-axis we have the absorbance. And if this is the 0 wavelength and it goes to 800 typically. So if you see a peak, so this is the spectrum's dead, and if you see a low intensity to medium intensity peak like this one, and this is at 200, let's say, suppose, that means that this peak is due to the n to sigma star transition because of its low or medium intensity, and second indication is that it appears less than 220 nanometer. Now, what kind of functional groups give rise to n to sigma star transition? That can give us clue to detect what functional group is present in that molecule, or what functional group can give rise to such type of a spectrum. So amines, they contains NH2, and the nitrogen contains the lone pair of electrons, and they can give rise to n to sigma star transition. Alcohols like amines, they also contain free lone pair of electrons on oxygen. They also can give rise to n to sigma star transition. Ethers, similar to alcohols, they also contain unpaired of electrons on top of oxygen, and they are capable of showing the n to sigma star transition. Thiols like alcohols, they are also rich in electron density, and they do possess the free lone pair of electrons. So amines, alcohols, ethers, and thiols, these 4 functional groups can give rise to n to sigma star transition. Why? Because all of these functional groups possess free lone pair of electrons on the heteroatom, nitrogen, oxygen, or sulfur. So this is the key information that can be obtained from the UV visible spectrum. So if you see a spectrum and see a peak at around 200 nanometer and the intensity of the peak is low or medium, then you should think about either this spectrum belongs to alcohol, amine, ether, or thiols. And thiols are possibilities, provided the non-bonded electrons are not included in conjugation system. This is main important. An exception to this generalization is that n to pi star transition of cyano group appears in this region. So sometimes the cyano group also appear in this region. So cyanide or nitrile group, it also contains nitrogen having free lone pair of electrons, and it can give you n to pi star transition. So n because of the free lone pair of electrons, and pi because of the pi bond present in the triple bond between carbon and nitrogen. However, this is a weak transition, less than 100 molar absorptivity, and the cyano group is easily identified in the IR. Do not neglect to look for NH, OH, CO, SH bands in the IR spectrum. So spectroscopy is a correlated techniques. Sometimes you get good information from the NMR, sometimes you get good information from the IR, and sometimes you get decent information from the UV, but the least information that you get it from is from the UV, and the maximum information that can be obtained is from the proton NMR. So all of these spectroscopic techniques, they are interrelated with each other. They can be correlated with each other, and they can be jointly used as an evidence for structure elucidation. Let's go back. Move on and look at the Guideline II. If you see a single band of low intensity around 10 to 100 in the region of 250 to 300 nanometer with no major absorption at shorter wavelengths 200 to 250 nanometer usually indicates N to pi star transition. Again, let me draw the UV visible spectrum. So on the x-axis we have the lambda max in the wavelength in nanometers and absorbance and the molar absorptivity on the y-axis. So you have a spectrum tick, 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 and you see a peak at around 250. This is a peak at around 250 or to 360 nanometer. So the peak is in between 250 and 360, and the intensity of peak is not much. It's a low intense peak. This indicates that this peak is due to the N to pi star transition. Since the absorption does not occur at long wavelength, a simple or unconjugated chromophore is indicated, generally one that contains oxygen, nitrogen or sulfur atom. Examples of this may include carbonyl group, carbon double bond nitrogen, nitrogen double bond nitrogen, because they all contains free pair of electrons. And there's a pi bond, so hence they are showing N to pi star transition. So all carbonyl groups give rise to N to pi star transition, that's sure. And if there is a double bond and the heteroatom, they will give you the N to pi star transition. So N because of the free unpaired electrons, pi star because of the presence of a pi bond. Let's go to the Guideline 3. Two bands of maximum intensity 1000 to 10,000, both with lambda max above 200 nanometer, generally indicate the presence of aromatic system. This is how you can identify that there's an aromatic system. So aromatic system means there's a benzene ring or any heterocyclic which are aromatic in nature or naphthalene. So aromatic is usually this sort of. How we can detect benzene? There should be two bands of medium intensity having intensity from 1000 to 10,000, and the lambda max should be greater than 200. That generally indicates the presence of aromatic system. If an aromatic system is present, there may be a good deal of fine structure in the longer wavelength band in non-polar solvents only. So don't forget that there's a huge impact of solvents in the UV visible spectroscopy. I have made one video about what is the effect of solvent on my YouTube channel. If you are not familiar what is the effect of solvents on the spectrum, then please go and watch that video in order to understand what is the effect of solvents on the UV visible spectrum. And substitution on the aromatic rings increases the molar absorptivity above 10,000 particularly. So for example, this is benzene. If you substitute this benzene with any electron donating groups or with trying groups, they might increase or decrease the wavelength of this benzene depending upon the nature of the group. If polynuclear aromatic substance, a third band appears near 200, so like two benzene rings are there, three benzenes, that's called polynuclear. A third band of 200 nanometer, a band that is in simpler aromatics occurs below 200 nanometer, where it cannot be observed. Most polynuclear aromatics and heterocyclic compounds have very characteristic intensity and band shape, fine structure patterns, and they may often be identified via comparison to spectra that are available in the literature. The textbooks by Jeffrey and Orchin and by Scott, which are listed in the references at the end of this chapter, are good sources of spectra. Guideline number 4. Bands of high intensity 10,000 to 20,000 that appear above 210 nanometer generally represent either alpha beta unsaturated ketone, you can take help from the IR, a diene or a polyene. The greater the length of conjugated system, longer the observed wavelength. So if you are not familiar with the topic, what is the effect of conjugation on the ultraviolet spectrum, then please go into my YouTube channel and watch the video about what is the effect of ultraviolet spectrum. Now, what is the effect of conjugation on the ultraviolet spectrum? For dienes, the lambda max may be calculated with Woodward-Fieser rules. Number 5, guideline number 5, simple ketones, acids, esters, amides, and other compounds containing both pi systems and unshared electron pairs show 2 absorptions: an N to pi star transition at longer wavelength, greater than 300 nanometer low intensity, and a pi to pi star transition at shorter wavelength, less than 250 nanometer high intensity. With conjugation enones, the lambda max of the pi to pi star bands moves to a longer wavelength and can be predicted by Woodward's rules. The epsilon naught value usually rises above 10,000 with conjugation, and as it is very intense, it may obscure or bury the weaker N to pi star transition. For alpha beta unsaturated esters and acids, Nielsen's rules may be used to predict the position of lambda max with increasing conjugation and substitution. Rule number 6 and rule number last. Compounds that are highly colored, have absorption in the visible region, are likely to contain a long chain conjugated system or a polycyclic aromatic chromophore. Benzenoid compounds may be colored if they have enough conjugating substituents. For non-aromatic systems, usually a minimum of 4 to 5 conjugated chromophores are required to produce absorption in the visible region. However, some simple nitro, azo, nitroso, alpha diketo, polybromo, and polyiodo compounds may also exhibit color, as many compounds with coinide structure. So this is a coinide type structure. These are the 6 guidelines which may help you guys to interpret the ultraviolet spectra, and you can use these guidelines to take information and take as stepping stones to assign the ultraviolet spectra or interpret them or get information from the spectra. And I will end this video here. Thanks for watching. Take care. Goodbye.